Zero. That is the number of patents on record for this. Zero. For a greenhouse gas that is 273 times more potent than CO2.
And it's not like the gas is rare. Agricultural soils are responsible for about 60% of all human-caused nitrous oxide emissions globally.
Okay, so here's the wild thing. We've been so focused on carbon that this other greenhouse monster has just been sitting there in the dirt, literally, and nobody has built the dedicated machine to deal with it.
The dirt, fertilized farm soil just off-gassing continuously, and we have, checks notes, nothing commercially aimed at it.
To be precise, there's no mature scientific or commercial pipeline specifically for electrochemical N2O reduction using copper single-atom catalysts in distributed on-farm reactors. That's the gap.
Which, dumb smart question. What even is a single atom catalyst? Like, genuinely, what are we talking about?
So instead of a surface covered in copper atoms all jumbled together, you have individual copper atoms, each anchored to a support material, usually a carbon matrix. Each atom is its own active site.
And that matters because you're getting maximum use out of every single copper atom. You're not burying atoms in the bulk where they do nothing.
It's like the difference between spreading butter with a whole stick versus actually using the surface. Every atom is doing work.
That's a reasonable analogy. And the chemistry here is genuinely favorable. The reduction of N2O to plain nitrogen gas is thermodynamically downhill. The standard potential is plus 1.77 volts versus the standard hydrogen electrode.
Which means, and this is the part that got me, the report suggests the energy economics could potentially be 3 to 5 times better than CO2 reduction reactions, once selectivity and mass transport problems are actually solved.
Wait, so it's actually easier to fix than CO2, and we've been ignoring it?
Thermodynamically easier, yes. But that's the theoretical floor, not the finish line. The challenge is selectivity and getting the gas to the catalyst surface fast enough, mass transport. Those are real engineering problems that haven't been cracked yet for this specific application.
And there's a paper, Zhu et al., Nature Energy, 2020, that established the key mechanism, the dynamic cluster formation behavior in copper catalysts, and it has 683 citations. So the foundational science is there, even if it's pointed at adjacent reactions.
683 citations, and still nobody has pointed it at the actual farm problem. That's a gap that's almost hard to believe.
The research database KPsphere analyzed 176 sources, 101 papers, shows all the adjacent work. Copper single-atom catalysts for CO2 reduction, for nitrate reduction. The N2O work is being constructed by analogy.
And the funding picture is striking. Total tracked federal funding in the adjacent space, $9.8 million. None of it explicitly targeted at this.
9.8 million is not a lot of money in the context of climate tech. That's a rounding error on a battery startup Series A.
Right? SUNY Albany got $464,000. University of Maryland got $550,000. These are small grants doing adjacent science, not a coordinated push.
So why does this matter beyond the obvious greenhouse gas angle? The distributed on-farm reactor concept is the interesting part. You're not proposing to capture emissions at a central facility. You're talking about small electrochemical units that sit on individual farms.
Which is a completely different infrastructure bet. It's like the difference between building one giant power plant versus putting solar panels on every roof.
And agriculture is already wired up in a lot of ways. Sensors, precision farming equipment. Slotting in an electrochemical abatement reactor is not insane from an integration standpoint.
Though the power requirement on-farm is a real constraint. These reactors need electricity, which is either grid power or on-site renewable, and that cost structure has to pencil out against the cost of doing nothing.
The wild thing is, because N2O reduction is thermodynamically more favorable, you could actually be running these reactors more cheaply per unit of warming prevented than any CO2 capture technology currently operating, if the selectivity gets solved.
That if is doing a lot of work. Selectivity is unsolved. Mass transport is unsolved. Even capturing diffuse soil gas and concentrating it into a reactor-compatible feed stream, that's arguably harder than the catalysis itself.
Which is exactly why the first mover window is estimated at 18 to 36 months. China is disproportionately represented in the high-impact copper single-atom catalyst papers. 11 records, but they're punching above their weight in citations.
So the US has more records, 60 versus 11, but China might be ahead on the specific catalyst architecture that would actually matter here.
And 0 patents claimed on this specific application from anyone. US, China, EU. Nobody has planted a flag.
That's the opportunity geometry as the report frames it. The fundamental electrochemistry is favorable. The catalyst class is understood from adjacent work. The target gas is abundant and essentially unaddressed, and the IP landscape is empty.
Okay, this is where it gets really interesting to me. Normally, when you see a gap this obvious, it's because there's a hidden hard problem that everyone already tried and gave up on. Do we know if that's the case here?
The report doesn't surface a graveyard of failed attempts. It reads more like genuine neglect. Everyone chasing CO2 because that's where the policy and the funding pointed.
N2O doesn't have a Paris Agreement moment. It doesn't have a carbon credit market with real liquidity. So the research incentive structure never tilted toward it.
Which means whoever builds the market mechanism, the measurement, the credit, the verification, might matter as much as whoever builds the reactor.
That's a clean way to put it. The chemistry gap and the market gap are both open at the same time.
And the regulatory tailwind is building. The EU's pending revision of the Industrial Emissions Directive and the US EPA's 2025 N2O reporting framework are putting agricultural emissions increasingly in scope. That creates a compliance demand that doesn't fully exist yet, but is forming.
So you've got thermodynamics that works, catalyst science that's close, 0 patents, empty IP, no commercial pipeline, and a regulatory wave coming. That's a lot of unlocked doors in one corridor.
The 18 to 36-month window before incumbents pivot is the number I keep coming back to. That's not a lot of runway.
Incumbents here being large agricultural chemistry companies and the electrocatalysis groups that already have copper single-atom catalyst programs running for CO2. Redirecting is not a heavy lift for them once they see the signal.
The fact that the signal is this legible right now is kind of the whole point of flagging it.
273 times worse than CO2, 60% of human-caused emissions, 0 patents, thermodynamically favorable, but with real engineering problems still to solve, and an 18 to 36-month clock. That's the summary.
I'd want to watch the selectivity research specifically. If a paper drops solving that problem, the reactor engineering could move very fast behind it.
And watch China's publication rate in copper single-atom catalysis. They've been outpacing on impact already. If they connect that work to N2O explicitly, the window shrinks fast.
Full deep research, 176 sources, all the funding records, the full methodology. That's at kpsphere.com/research.html. We'll be back with another one soon.
The dirt is trying to tell us something.
It has been for a while.